Good morning, everyone. Welcome to our seminar series. Today we have Zhao talking about applied mathematics in the field of asteroseismology and I believe binary stars and maybe even beyond that. We'll see in the talk. Zhao did his PhD in the United States, I believe Georgia State University. Then he spent a couple of years as a postdoc in Poland, another couple of years at the University of Pennsylvania, I think, and then moved to Cambridge for 3 years to work on theoretical asteroseismology. Since 2024, he joined Connie's team to work on the 4D star project that everyone, I think, in this auditorium have heard already 155 times by now. Right, Connie? Or was it the right number? Anyway, enjoy the talk on the applied mathematics. So the floor is yours, Zhao.
Great. Thank you very much, Andrew, for the introduction. So thank you all for coming to this seminar. So I'm going to talk about applied mathematics. There will be equations shown. So on the left, we have different branches in mathematics or applied mathematics. On the right, we have some fields or subfields in physics, which are closely related to asteroseismology. And then you can see as an asteroseismologist, I'm both Fourier-centric and asteroseismology-centric. But I hope if we can explore a little bit outside our field, we can get some benefits. So let's start with the Stokes theorem, which is the theorem we learn in undergraduate courses. So basically, we have a line integral, or the circulation of this vector field f, which is equal to the surface integral of the curl of this f. So we all learned this theorem, but if we think of this closed surface or the closed curve and the projected stellar surface, stellar disk on the sky, we can say, okay, we have the vector norm n here. We have this vector field, the curl f here, pointing outside the plane. So if we want to calculate the brightness of star, we simply integrate this vector here in the circle here. So you may say, okay, maybe, but the star is limb darkened. Well, of course, we can use simple linear limb darkening law. How this coefficient, this coefficient is different for different type of star and often for different evolutionary stage of star. Here, showing the temperature and log G plane for different evolutionary tracks. Of course, the star is more limb darkened for the giant stars, of course. So now the goal is to find the vector field f, whose curl is this linear limb darkening law. So this can be easily done. So we can write this intensity of the star as like function x and y, and then solve this differential equation to get the f. There can be many different f, but we can only pick any one. And then this integral, we can just integrate this line integral here, the circulation, around the limb of the star here. So in the end, we end up with this integral, which is solvable analytically. So we have analytically complete form. We have closed form for this expression, which is very fast and very nice. And this is taken from Andreas Paul's paper in 2012. Okay, so and then you may ask why should we care about this? So the point is, in some cases, in some scenario, maybe let's say multiple eclipses or multiple transits, we have multiple objects. And people usually like discretize the surface by many segments and for each object, and then numerically integrate each surface. But if you use this simple technique, you can transform this into this line integral. You only need to integrate along this limb, the star, or different stars. So this is extremely powerful in this case, and we can have an analytical solution for these line curves or multiple transits. So this is very nice. So and this technique has been later improved by calculating the radial velocity curve as well in multiple transits and multiple eclipses. And if you use this code and use this method, and with n-body code, you can have a photodynamic modeling. This has been applied to the like exoplanets around binary stars. So this is very nice. So the benefit is that this is very, very fast. You don't have to integrate your surface. So there's another application of Stokes theorem. In this case, we have the magnetic field, the star. Let's say the sun. We have usually have spot groups. Usually have two polarity, like this is the south, this is the north, and the magnetic field line is pointing around this line. So basically, we are having kind of like toroidal magnetic fields. Like essentially, we have a B phi dominant field on the solar surface. So now we can use the Stokes theorem. We take a contour, which this contour is in the convection zone of the star. This is a meridian plane, like this plane. And this contour, so if we want to calculate the toroidal magnetic field flux, which is essentially the B phi integral, B phi for this surface integral, you can convert this to a line integral by using the induction equation. And then in the end, you end up with a line integral. So you only need to integrate the surface element, which is a D element here. So this will finally become this very, very, very nice form here. In this paper, Cameron applied this technique and calculated the magnetic field flux for the sun. So here, the theoretical predicted magnetic flux is a solid line here. There are northern hemisphere or southern hemisphere for red and blue. But we also have observed magnetic flux, which are the dashed line here. So these two, you can compare the two, which is kind of like in reasonable agreement. And this ended up in a paper on Science in 2015. So you can see we can apply this simple Stokes theorem and a published paper on Science. Okay, so now back to the main stage of this talk, which is the asteroseismology. So let's say we have some fluid in the star. We can displace the fluid. We have the displacement, deperturbation, also the velocity. So we can simply use, say the mass is conserved, which is a continuity equation. We can say, okay, maybe let's assume they're adiabatic, there are no heat exchange. We have the adiabatic relation. We have the Poisson relation, which keeps star. And then we finally have the Newton's second law, which is the equation of motion. So we linearize this. We get this linearized equation. We put everything, let's say rho prime, p prime, and phi prime into this linearized equation of motion. We get this eigenvalue problem, which have the linear operator L acting on the eigenvector psi and then eigenfunction omega squared, and again, eigenvector psi. So we have a pair. So basically, we are having this kind of oscillation equation for adiabatic case, no rotation, no magnetic fields. So now we can perturb this operator. So like the delta L, and then your eigenfrequency and eigenfunction are also perturbed. Let's say we can have different kind of perturbation. Like maybe this perturbation is due to rotation, maybe due to some mean field in the in the mean flow in the convective envelope, or maybe some active regions, maybe some sunspots, or maybe some non-adiabatic effect, or maybe magnetic fields. So this perturbation can be small, also can be large. So that's basic equation. We can also do some engineering. We can put a right-hand side a source term, and this source term can be a tidal force from the companion star. It could be like stochastic forcing, just like the Reynolds stress in the solar-like oscillator driving scenario. The right-hand side can also be like a nonlinear term, like a quadratic nonlinear terms, or cubic nonlinear terms. So let's start with rotation. Okay, so now the perturbation to the vector, to the operator, is essentially a mean flow U0, which is essentially induced by the rotation. So we have now a perturbation to the eigenfrequency, which can be written like written as the kernel times the rotation rate. So to the first order, we all know that the L equals 0 moles split to 3 moles, L equals 2 moles split to 5 moles. They are nearly equally spaced. The spacing is approximately 1 minus some constant times the rotation. So we also have the perturbation. We have the perturbation to the eigenfrequency. We have the perturbation to the eigenfunction. This would be very nice. But this first order approximation can only be applied to slow rotating stars. So maybe the second case, The second case, our perturbation to the operator is some mean flow. This has been used for detecting the convective flow in the solar interior, especially in the convective envelope in helioseismology. Okay, maybe the third case, we can have some sunspot effect, and we can model the changes caused by the sunspot to the stratification and the positive change of the sunspeed, c square here. Okay, so now the operator changes is like this. And finally, in the fourth case, we have a non-adiabatic effect. Now this perturbation to the operator is the Lagrange perturbation to the energy generation rate and also the divergence of the energy flux. So basically, you can use this to study essentially the epsilon mechanism or to infer the mode damping rates or driving rates. And also, like the fifth case, magnetic fields. I'm sorry about the equations, but the point is we have an operator perturbation, which is a perturbation to the Lorentz force here. So we do the same inner product here, of course. This is a little bit nasty, but it has many different terms. But if we keep the dominant terms, let's say for the P modes, we have the dominant term, which is essentially the radial displacement derivatives. We have the term here, which, okay, using integration by parts, you can have this two term becomes the psi r derivative squared, just like this. This is for P modes. For G modes, the dominant term is the horizontal displacement. So we have the similar expression, which is how the horizontal displacement derivative squared here. And all the angular integral has been included in the constant d, constant c here. So, okay, you may say, okay, we want to keep all the terms here. Okay, if you want to keep all the terms here in this inner product, a nice way to do this is to expand your magnetic field and expand your velocity field in spin-weighted spherical harmonics, which is better than normal vector spherical harmonics. And you work out all these vector or tensor operations, and finally you can separate out all the effect on the magnetic field. So here is the magnetic field, which is like Lorentz stress tensor, B, and then we have a kernel here. So this has also been applied. This technique has been applied to a few different right giants and different cases. So observationally, so we have this nice detection of magnetic field from the dipole J-dominated mixed modes. So basically, we have rotational splitting and magnetic field splitting all together. If we combine, the magnetic field tend to shift your prograde and retrograde mode to the right by the same amount. Then you have then in the end, you have a larger spacing on the right and smaller spacing on the left normally. So this has been used to detect the magnetic fields, which is near the core of right giants, which is like 30 kilowatts to 100 kilowatts. This is a paper from Gang Li. So also this perturbation to the magnetic field, the perturbation to the frequency scales with 1 over omega cube. So you can see in this diagram, in this HL diagram for periods, if we move to lower frequency, we have a larger spacing. This is larger frequency shifts as expected here from this scaling. Okay, so maybe you want to write down your perturbation in the full form. So this is actually the basis of asteroseismic structure inversions. So you can use different pairs. We normally only need 2 pairs of structure, like a rho or sunspeed square, or you can convert to other different pairs, which are listed in this table from Gale's thesis. Or some of the kernels need a little bit more work, like this A kernel, which is directly related to the Brown frequency squared. You can also perform an inversion for global parameter, like a mean density, acoustic radius, or some edge indicator, which is related to the sunspeed gradient. So maybe in some cases, we want to use the combination of frequencies. So say we have a sort of like oscillating star, we have usually a lot of different P modes here. Okay, we already know, okay, the spacing between adjacent radial order we call large separation, delta nu. We can define some small separation, like say the closest, let's say this one, delta nu 02, which is spacing between the closest L equals 2 and L equals 0 moles. We can define the delta nu 01, which is the distance between L equals 0 mode and the middle line of the 2 L equals 1 mode here, this dotted line here. Usually people define the small separation ratios, like say small separation divided by the large separation to get rid of all this global set parameter effect. I use these ratios like R01, R10, or R02. So this kind of ratios can be used to infer the interior, especially the core properties, or the and as I can show here, here are the three R ratios here for this kind of solar type star, like J star. You can see this R01, R10, this line, there are some wiggles. Actually, this periodicity in this R0 ratios, actually, this small separation R01 ratios is closely related to the glitch features in the star. And for example, delta mu 01 has been used to infer the base of the convective envelope in the solar type stars in Roxburgh. And also, the delta nu 02 has been used to infer the core properties, like especially the sun speed gradient. And on the right, we have also delta nu 01, which is from a model for Uranus from a recent paper. So actually, this periodicity or this in this delta nu 01 is closely related to the core signatures, because this model of Uranus has a solid core which the sun cannot penetrate. So essentially, if you do a Fourier transform of this diagram, you get a peak which is closely related to the core signature. Okay, so this is very nice. We can use combinational frequencies or small separations to infer the stellar interior. But to better show the glitch features in the sun or in the star, let's do some engineering to this famous chain supermarket in the US. Maybe it's not so famous here in Europe. So after some engineering, we have a stellar structure for solar type star, for the F-type star, for the ABO type stars. The red regions are the convective zone. So we can see for solar type stars, okay, we have a convective envelope. We have a helium ionization zone, which was shown here in the for the gamma. We have the bottom, the convective envelope here. For the massive or intermediate or massive star, we have a convective core, where the convective core boundary can also act as a feature to generate glitches. So basically, these glitch features can act as some kind of localized scattering potential, which will generate your oscillatory component, your frequency in your periods, just like what we show here in this diagram. So we can have acoustic glitch or buoyancy glitch. Okay, so to study this, we can use some techniques in quantum mechanics. Let's say we have some incident wave from left-hand side, which is propagating from left to right. And then we also have some localized potential, let's say acoustic potential or a buoyancy potential. So actually, the total wave function and R is the sum of the incident wave and the scattered wave. So the incident wave satisfies the homogeneous wave equation, and the total wave function satisfies the inhomogeneous wave equation with the potential on the right-hand side. It is well known that this equation can be solved by using Green's function. If we replace the right-hand side by a delta function, and then your final solution will be the incident wave plus the convolution of your potential with your Green's function here. So, okay, we arrive at this expression. We can give you this wave function here and R. Okay, this is the integral equation for psi. You can see psi is here, psi is also in the integral. So why bother? So we are making things worse. Actually, this equation can be discretized and solved by a matrix method, or you can approximate this by using the Born approximation or Born series. So essentially, you are replacing this psi with this psi. You plug this whole equation into this again, and you get this series. This is a very commonly used approximations, like Born approximations. Let's say, okay, this is basically what I have been said is on the right-hand side here. Now, for the asteroseismology, we have P modes and G modes. Okay, for acoustic waves, we have a very similar equation. Another kind of like Schrodinger type equation. We have a potential here, V. We call it acoustic potential. For the gravity wave, we have a buoyancy potential. This is very similar. So again, we can use the Green's function, like the G here. We can do the convolution. We can get our final solution, which is very essentially the same as this equation. But before we do this, we need to carefully convert our variables. Let's say for the acoustic wave, we need to, our x coordinate is just the acoustic radius or acoustic depth. And for the G mode, our x coordinate is the buoyancy radius. But this is very nice. This is a very nice analogy. You can solve this by using this Green's function. So after we get this solution, ignore all of this. Just focus on this rectangle here, we can do some asymptotic analysis for this solution, and we can write down the solution and the sign function and get this phase shift, delta. This phase shift is directly related to the small separation, delta nu 02, or you can say delta 01 also. So essentially, we can have a closed expression for the small separation. So in Roxburgh, how we use this Born approximation for L equals 0, 2, also L equals 1, 3. There's two small separations, which are very nice agreement between the Born approximation and the exact numerical values. And also, this is much better than the normally used asymptotic solution for delta nu 02, which is just the integral of the sound speed gradient. Okay, so what if the glitch feature is large? So people in asteroseismology usually solve this by connecting wave solution in different cavities. Let's say, okay, we have normally in the star, we usually have a G-mode per cavity, which is essentially inside this Brand-Vasala frequency squared, and we have the P-mode cavity, we have some evanescent zone between. The solution inside the cavity, if it's away from the turning points, are essentially sine and cosines. If they are close to the turning points, like just here, they are essentially the Airy functions, Airy type solutions. And in the evanescent zone, which the solution is essentially exponentially decreasing function. So we can essentially connect these two solutions and get our final oscillation frequency expressions. Okay, so this has been done for subgiants or red giants. On the left, we have two cavities for red giants or subgiants. We have G cavity or B cavity. And on the right, there are three cavities because this is a red giant undergoing helium flash. Because the helium flash is off-centered, we have this additional convection zone here, so which separates the original G-mode cavity. So we have three cavities here. You can connect the solution in the three cavities and get your eigenfunction or eigenfrequency relations. But the oscillation spectra for this kind of flashing star is more complicated, of course. So of course, you can essentially extend this all the way to n cavities as large number as you want. This has been done by Picon and Takata. So we have n cavities, and each interface we have some transmissive and reflective coefficients. And also for the cases if we have magnetic fields on rotation, like this is recent work by Lucas. If we have a star, let's say a gamma dwarf star, we have a commutative core and radiative envelope, and it's rotating. And in the radiative envelope here, we have the gradual inertial with the inertial gravity waves. I'll say inertial gravity wave the G cavity, which is described by the Hall function. And inside the commutative core, we have the pure inertial mode, which are essentially have this kind of brine solutions. You can connect these two solutions and interface and work out your period spacing, and which will generate a dip in your period spacing and period diagrams. And by the way, this is the pure inertial mode inside the commutative core. which are usually described by two quantum numbers. And also the pure inertial modes have a singularity belt, which is along the direction of the described by the spin parameter here. Okay, so in some other stars, like SDB stars, we have some well-structured envelope, mantle, and core. Let's say if we plot the Brown frequency, Brown-Vasala frequency, which is here, we usually have some bump or a spike due to this structure or the chemical discontinuities. Sometimes if the mode has a node near this bump, the mode can be trapped. And the two bottom plots are showing this kind of weighting functions, like whether the modes are concentrated by this single region. And for this is a trapped mode, this is the normal mode. So actually, we can also connect the solutions. Let's say Margarita has a paper which connects solutions on both sides of the glitch in the Brown frequency profile and get your buoyancy glitch or buoyancy frequency relations. Okay, so I'm sorry about all these equations, but now I'm going to do some engineering to the right-hand side of this equation. We add a source term, and I mentioned this source term can be a tidal force. Okay, let's say this tidal force can be a harmonic forcing from the companion star, which is the sum of the optical forcing, which is integer, which is n times the optical frequency. So basically, we have this equation. We can solve this equation by simply expand our solution as a sum of eigenfunctions from adiabatic eigenfunctions with some slowly varying amplitude c. So around this equation for c, which has this very this closed analytical form. So we have this tidally forced mode. We have the amplitudes predicted. We have the predicted amplitude and also the phases. So of course we have a lot of Harvey star observed by Kepler or TESS, which we can apply this to the tidally forced waves. So now we can do some engineering to the right-hand side. Now the right-hand side is a nonlinear term. Let's say we keep the quadratic nonlinear term here. So we do the similar stuff, expansion of the solution and the eigenfunctions, and with a slowly varying amplitude Q. Now you plug in this to this ansatz, you get this amplitude equation for a three-mode coupling case. In this three-mode, like a resonance three-mode coupling case, well, we have this frequency relations here. And this equation is relatively simple ODEs, and the only difficult part is just the three-mode coupling coefficient term here. But this essentially depends on the integral of three spherical harmonics, which will naturally give you some selection rules because only in this case you can get a non-zero coupling coefficient. By the way, this three-mode coupling is ubiquitous. You may okay, so let's say you may already experience three-mode coupling here because I didn't realize this laser pointer is green. But anyway, if you have been doing stargazing, you have already had some first-hand experience because the red laser or infrared laser is easy to make. Usually, to generate a green laser, you need some nonlinear crystal and use the second harmonic generation. This is kind of three-mode coupling. So basically, what is green laser is the result of three-mode coupling here. So this is the case of direct resonance, which means we have two low frequencies here, generate a third frequency or higher frequency, a third frequency which are higher. So we have some observations in the three-mode coupling. This is called direct resonance. These are like three p modes coupling to each other. If you plot the amplitudes of these two modes, A and B, and also the C, you can see this satisfy this very nice relation, where the scaling depends on your coupling coefficient, also the resonance or your detuning in the resonance. So we also have some evidence of three-mode coupling in SDB stars or subdwarf B stars as well. So another case for three-mode coupling is called parametric resonance. In this case, we have one mode here, which is unstable, it's driven. And then we have two low-frequency modes satisfy this relation. So let's say this is the power spectrum from a dead Schooley star. We only see one P mode. We didn't see omega A and omega B here because they are very, very high L G modes somewhere here, which are not visible. So the best daughter mode pair is actually with L from 50 to 200 for this case. So this is not possible to see, actually. So this parametric resonance can act as an amplitude saturation mechanism to saturate the amplitude of this mode. Yumin Li has calculated the saturation amplitude for SPB star solely pulsating B star. We gave you some very reasonable luminosity perturbations. And Jimbowski calculated for dead Schooley star P modes. And also there are some other papers talking about the different mode behavior when the three modes couple to each other. So indeed, in this three mode coupling case, this mode behavior can be very different. It can be chaotic. This is the mode amplitude, or one of the mode. It can be in limit cycles, depending on essentially two parameters. One is the detuning, like how far away this is from the perfect resonance. And the second is the damping rate ratio, which is essentially the damping rate of the daughter divided by damping rate of the parent. So we can have different type of mode behavior. We can even have chaotic or unbounded or pure doubling all the way to chaos. So you may have seen this kind of bifurcation diagram before. This is the peak amplitude of the mode, and this is a parameter, the damping rate ratio, which I mentioned before. By slowly changing your damping rate, like essentially daughter divided by parent, you can the system can have different behavior. You can have pure doubling, period 2, period 4, period 8, all the way to chaos. And inside the chaotic region, you may have periodic region. So now we can do some engineering. And to the right-hand side, now we keep the cubic nonlinearity term. So we have now this has formal coupling. Essentially, we have this frequency relation here. This can be applied to the L equals 1 triplet, like rotation split triplet, because we naturally have this resonance condition for the frequency in the splittings. In this case, the mode behavior depends again on the detuning, like detuning delta nu, also on the damping rate. So actually, there are three different regimes for this kind of formal coupling. The first regime is kind of stable regime where the detuning is very, very small. In this case, we have stable amplitude. In the second case, if the detuning is approximately the same as the damping rates, the system will undergo this kind of modulation, and this modulation in amplitude and frequency. The modulation time scale essentially 1 over delta nu, 1 over the detuning in the frequency. And finally, we have the third regime, which is the non-resonant regime. Essentially, if the detuning is very, very large, essentially we have 3 individual modes. I'm sorry about some of the text. Actually, after talking about 3 mode and 4 mode coupling, we can do a little bit better. Like we can write down the nonlinear wave Hamiltonian. We have linear wave and nonlinear part and linear part. The interaction part, the wave interaction Hamiltonian, which including the 3 wave interaction, 4 wave interactions. So we can write down the famous Hamilton equation. We all learned it from classical mechanics. If you use some variable transformation, you can convert this 2 equation to 1 equation, which is essentially this equation, and A is the wave amplitude. So we have, if you have some Hamiltonian, you already have this equation motion for your wave amplitude. So this is called the kinetic equation for wave amplitude. So if we square your your wave amplitude, you get this wave action or essentially wave energy, very, very closely related. You can get this equation for wave action n here, which is describes how the waves interact with each other. This equation is in Fourier space, so it's different wave vectors. So why are we doing this? Because if we do this for a large sample of waves, we can do some. If we assume the waves have random phases, we can do some ensemble averaging. We can find a stationary solution for this wave action A. If we assume that the wave action A is scaled with the frequency of wave vector to some kind of power law, after we get a solution, we may find the stationary power law for A and B. So we will have a stationary slope in the power spectra. So this can be done for the ocean gravity waves. So in the ocean gravity waves, essentially these ocean gravity waves are generated by the wind on the surface and also the tidal force. So the wave interaction is essentially the three-wave interaction is the dominant mechanism which can generate your equilibrium power spectrum. So actually, there is a universal power law spectra for the internal gravity wave in the ocean. Let's say this is the power spectra and the function of wave vector or wave number, vertical wave numbers with some slope. So this spectrum is called the Garrett-Monk spectrum. So actually, this spectrum, ignore all this text, I'm sorry. Just focus on here. This power spectrum has a slope of -4 if we enter the high wavelength, high wave vector tail. Essentially the power index is 4. The exponential index is -4 here. And this all this previous calculation, this kind of calculation give you essentially, this should be minus 3.7, which is very close to the observer spectra. So essentially, we can have a framework to calculate your power spectral slope in your gravity waves for the ocean gravity waves. Okay, so now I'm stepping outside our subject and talk a little bit about mechanical engineering. Let's say we have some kind of optimization problem. It's called a topology optimization. So we have a working domain, which is essentially a 2D beam. We want to do some optimization. We want to maximize the structural stiffness. We want to keep the volume half. We can keep half the volume, just like this or like this, and then we maximize the structural stiffness. We also maximize the J's natural frequency. So this is one of the fundamental mode of this beam. So if you solve this optimization problem, you can find your optimal structure for this 2D beam. So I wish we could do this for the star. But unfortunately, it probably is very difficult. Okay, so now I have talk all about these different mathematical techniques. Now I'm going to talk about some other things. Like this is one of the famous articles written by Nick Trefethen. You may heard about him because he has a very famous book on spectral methods. He has some favorite eigenvalue problems. For example, let's say maybe the first one is the Bay of Fundy in Canada, which gives you a 16-meter tide. That is world record. And the second, so any regular pattern you see in nature, probably maybe the cloud stripes or maybe some ripples on the sand, is some results of the eigenvalue problem because it is this eigenmode which grows faster than others. Then finally, essentially the leftover of the competition. This is another eigenvalue problem. And finally, I'm going to talk about a joke by Chandra. So this is a figure generated by GPT. So this is a birthday party held by Kip Thorne, one of the Nobel laureate in Caltech, and Chandra was visiting Caltech. And Kip Thorne was insisting on host this birthday party for him. And Chandra is sitting in the center here. We have some other people here, like Saul Tsiolkovsky, which is a famous numerical relativity expert. If you have used the rotating curve black holes. We also have the William Press, which is the author of the numerical recipes. So basically, they are sitting just in a dark basement, and then Kip was trying to keep the conversation going, and then Chandra said, "Let me tell a joke. How can we divide 16 lumps of sugar into 3 teacups, and each having a non-zero odd number of lumps? We have 3 teacups, 16 lumps of sugar. Okay, so there's silence, and then Saul ventured and said, okay, we can. This is probably not possible, and then okay, because the sum of three odd numbers is always odd, and then Chandra said, not at all. You can put 1 in the first cup, 1 in the second cup, and 14 in the last cup, and they said back triumphantly. And then Saul said, okay, 14 is not. 14 is an even number, and then Chandra said, okay, I would say 14 is an exceedingly odd number of lumps to put in a single cup of tea. So, so I will leave this, and thank you so much for your attention.
Thanks, Zhao. I think if we had prizes, which we, I guess, should establish roles for the next academic year, I think you would have high chance of winning one for the largest number of equations per square centimeter per second.
Yeah,
or something.
I'm very sorry. I should do better than that.
But thanks for the beautiful math. Questions? Time for questions.
Hi, Zhao. Thank you for your talk. I have a couple of questions, but I guess I'll stick to one. So, as far as I understand, when you use the linear force operator, you use it to get linear terms and to get the stability of solutions as well as the frequencies. And I would like to know your opinion about using nonlinear force operators. Do you use the same kind of thinking about it, or is it more complex?
Yeah, you can work out the similar stability condition by plugging into your exponential solution and check out the eigenvalues. And
so you use it for stability and the eigen functions.
Yes, we have. You can have the. I didn't show it here for the 3-mole coupling. For the false 3-mole coupling, you can have stability for this 1-mole solution or 3-mole solution. I mean, the technique is very similar to the normal 3-mole coupling equation. Is that the question?
How do you select at which order to stop?
Which to stop?
Yes.
Oh, I stopped already under quadratic or cubic term. So I work for 3-mole coupling. Of course, you stop under quadratic nonlinear terms. You just ignore all the rest. For 4-mole coupling, I only concentrate on 3-mole coupling, on the third order nonlinear terms. So, so essentially, you can include all of them. The way you made your mode coupling network large. Okay, so this is basically the wave turbulence equation I shown, which you can, but you don't want to solve all this equation. You want to do some averaging in the end. So, did I answer your question on?
Yeah, I think so. Yeah.
Okay. There's still time for questions.
Hi, Zhao. Thanks for a lot of really fun information. I was really interested in the beginning of your talk with these line integrals, where you showed their application for photodynamic modeling and also the modeling of the spot modular, or not the net toroidal flux on your star. I was wondering if you can apply this to the case of the modulated observed amplitude of pulsations when you have an eclipsing binary. So right, you normally have your disk, and then when you have the eclipsing binary, you preferentially block out parts of the star, therefore modulating the.
Yeah, well, simply, well, if you replace this Lim-Duncan law by spherical harmonics or some kind of combination of that, I think you can do that. I don't know, but I think you can do that.
Because you should be able to do this in two ways, right? So you have your line integral describing the surface and your limb darkening, and then you have the original that's acting as a filter for the original spherical harmonics that are underneath it. So you should be able to get a time-dependent formulation of what the mode visibilities are for an arbitrary set of modes.
Yeah, this is doable, I think. Yes, that's a very good point.
That would be really helpful.
Yeah, I don't think anybody can try that yet.
Do you have time?
I don't know.
Thank you.
Let's see. Yeah.
Still have time for questions? I'll have a very annoying one for you, Zhao, I guess. I'm an observer.
Me too. I'm not around.
Yes, you're also an observer, but
Yeah.
doing a lot of theory.
Trying to.
How can we meet and start talking same language? For example, when you speak about nonlinear mode coupling, you have this elegant mathematical solution to the problem, and then you say, okay, we kind of observe this in stars as well. What do I learn from that?
You learn about essentially the mode damping, mode driving rates.
Let
essentially
me
by
what do you learn about the evolution of stars from that, or interior structure, or something about stars in physical terms?
Well, I think one of the applications you can think from the three-mode coupling, if you see some kind of three-mode coupling here, you may have observed frequency and phases. You can have this kind of inference on this kind of coupling coefficient, which directly give you this kind of detuning and damping rates, like the imaginary parts of the frequency. The detuning is evolutionarily dependent, of course. For different type of star, your mode density will be different. You may have very strong resonance for later evolutionary stages if your modes are dense. For the early star, you may have less strong, I should say, resonance, and this will change your coupling coefficient, and then eventually change your relation between your daughter modes and parent modes here. So if you plot this kind of observed relation, you may have different kind of scaling. We need to scale this red line to the black line, so you may have different scaling, which is kind of like an edge indicator. I mean, I should say it's a very, very slow varying functional edge, but I think in principle you can have a handle on the edge, if possible. For the mode damping rates, it also, of course, depends on the evolutionary stage of the star. And of course, when the three modes couple to each other, they settle into a stationary solution, and this solution is also edge dependent. So you may have some observed modes with some fixed amplitudes, maybe have lower amplitudes if the resonance is stronger, and higher amplitude if it's not so strong. We have been people have seen this in data scooting star for like older data scooting star or younger data scooting stars, I think. But it's a little bit difficult, but you can link this to observations if you work hard enough. Yes.
And this is something we can learn only from the observations theory of nonlinear mode coupling. We cannot learn these things from just normal modes.
On the normal mode.
Like, well, if we ignore the nonlinear coupling, for example, in our modeling, how wrong can we be?
You ignore the normal modes. You only if you get rid of all this combination frequency, you work only on the individual frequencies. I think most cases should be fine, except for the strong cases where the frequency shift due to mode coupling will be strong. Well, we have been doing this all along, right, for asteroseismology. So it's now. I should say it's okay to do that in most cases.
Okay.
Yes.
There is still time for questions.
So when you were discussing about the solution of the linear force equation, and you add the magnetic field as a source term, do you get a different solution as when you deal with the MHD equations? That's to say, you get also magnetoacoustic modes and Alfvén propagation?
I did not add the magnetic field and the source term, but only add the perturbation term to the linear operator L. So it's a perturbative approach, and there's no resonance to Alfvén wave, so you will now get that here by this approach. So this is a very simplified, it's a very approximate way of calculating frequency shifts.
So is it used more to separate the degeneracy of P modes?
Yes, I mean you can this probability method you can. I didn't show it here, but your frequency shifts can be written for a different m, and you can work out the perturbation of the linear operator and the inner product. This kind of term can be written as a matrix. I mean, Vincent also Yella is working on this kind of thing, and so I mean, what I'm showing here is a rotationally dominated, simple perturbation treatment thing. Yeah.
We still have time. Maybe one more quick question from me. So, to be honest, you lost me a little bit halfway through the talk. Maybe the answer was towards the end of the talk to my question. But what I know about 4D star is that, you know, it's about doing stars in 3 spatial dimensions and 1 time dimension. Right?
Yes.
So what ingredient in your talk reflects on the upgrade from 1D to 3D or 4D?
Yeah, I mean, there we have 1D oscillation code, 2D oscillation code. By assuming the phi azimuthal angle is always the symmetry is kept. But of course, you can relax and you can have the 3D. So in mechanical engineering, people using finite element methods usually to study the eigenmode structure. They call it the model analysis. Study the stability of this eigen frequency of this beam or different kind of structures. But this or other kind of numerical method like finite volume or spectral element, you can. But just people are not so, I should say, dedicated to apply this method to stellar oscillation equations. So, I mean, in principle, you can do this kind of optimization by work out on a 2D domain or 3D domain. For the star, just we need some knowledge from other fields, I should say, or from numerical, or CFD.
Okay. Last chance to ask a question. If not, then let's thank Zhao again.
Thank you.
Thanks for coming. See you next week.